Everybody. Welcome to the second lecture of Daniel on BMO. Please, Daniel.
Okay, thanks a lot. Well, first of all, I already uploaded in the chat the transparencies, revised version of the transparencies. And also I uploaded this paper that I wrote 20 years ago on BMO, so where you can find the proofs that I'm not going to speak about. And yesterday we finished the talk. When we were finishing the talk, we started speaking about the duality theory. You remember that we said that we know that for p between 1 and infinity, the dual of hp can be identified with hq, where q is a conjugate exponent. But this is no longer true for p equal 1. The dual of h1 is not h infinity. BMOA shows up here. The dual of h1 can be identified with BMOA, analytic BMO, and this is the so-called Pfefferman duality theorem. The precise statement is this: we have a function in BMO and a function f in BMO and a function g in h1. Then we can say that this limit, the limit as r tends to 1 of the integral of over the torus of the conjugate of f times g r e I theta exists. And then if we define for any g, for any f in BMO, we define TFG as this limit, then this TF is a bounded linear functional in H1. And actually the node of this functional is comparable to the BMO node of f. And conversely, any element of the dual of H1 is of this form for some f in BMO. This is the Pfefferman duality theorem, and I'm going to sketch a little bit the proof, maybe. So let's see. Maybe let's start with what I say the easy part. If we have a function in the dual, a functional in the dual of H1, then we just use the Hamm-Banach theorem to extend it to a functional in L1. Since we know that L1, the dual of L1 is L infinity, then we obtain a function b in L infinity, so that Tg is the integral over the torus of the conjugate of b times f. Once that we have this, one has to do a little bit of work, and then we can prove, it's not very difficult, actually it's more or less standard, that T is going to be Tf for a certain function f, which is of the form f1 plus I f2, where f1 and f2 are analytic in D and have bounded real parts. Since they have bounded real parts, this function is in BMO. And so more or less, this is the easy part. I will not get into details. But maybe the more difficult part is the other implication. I'm going to present the proof, which is maybe it's not the most known proof. For instance, is different from the one that I presented in this manuscript that I have uploaded, and this follows the let me start recalling something which we are going to need in the proof, which is the so-called Hardy-Stein identities. The Hardy-Stein identities, well, this is an expression of the HP node of a function in terms of the integral of this function over the derivative. When p equal to, this reduces to the well-known Littlewood-Paley identity. But for other values of p, we have this. This is a classical result, and actually it's not difficult to obtain. We just have to take derivative with respect to r of the integrals mean of order p, and then more or less one get this, and it's not difficult to obtain. And actually, we are going to be interested in this Hardy-Stein inequality identity for the case p equal 1. So for the case p equal 1, the identity that we are going to use is that the h1 node of a function f is essentially this, the integral over the disk of the Jacobian of f, the f prime square over the absolute value of f times log 1 over 1 minus. So this is one of the ingredients that we are going to use in the proof. So I prefer to state it in the beginning, and let's see more or less how goes the proof. We are going to use an approach by Ness in a paper in the Bull of London Mathematical Society in 1983. Maybe this is not the most standard way to prove this theorem. And then actually what he proved is that using the subharmonicity of the function log of absolute value of f squared, and we add an epsilon, a positive epsilon, and Green's theorem, then we obtain a lemma which is due to Uchiyama. And this lemma due to Uchiyama is the following. If we have a real valued function, which is of class 2 in the closed disk, and actually is analytic, then if we integrate in the torus the absolute value of f times e to the raised to the power to f to 5, sorry, this is bigger than the Laplacian of 5 times e to the 5 times e. And this is just a computation using Green's theorem and using the fact that this function log of mod f squared is a subharmonic function. And using this lemma, then we can, this is the basic result to obtain what I'm going to call the basic result for duality. The basic result for duality is this. Now, if we have a function f in BMO A and a function h in H1, then we can obtain this one for the integral over d of the mod of f prime squared times the absolute value of f times the log of 1 over mods. This is bounded by a constant, which is e times the h naught, the h1 naught of h times the BMO naught of the function. So this is the what I call the basic duality result, and this is a consequence of the Uchiyama's lemma. And let's see more or less, it's easy to obtain the basic duality result, because what we do, we take this function f in BMO and this function h in H1, and then we construct this new function. We have the mod of f squared, and here we take the Poisson integral of the function whose boundary values is mod of f squared, and then we divide by the naught. Then, trivially, this is this is non-positive because this is a majorand of this, and is bounded below by 1. And a computation shows that the Laplacian of phi is 4 times the mod of f prime squared over the BMO naught of f squared. Since this is positive, the Laplacian is positive, we have here, this is positive, so we have that phi is harmonic. Then using the harmonicity and the fact that it's bounded below by 1, we get that, and we use the lemma, the previous lemma, the lemma that we had before. Then we have that the h1 naught of f is bigger than this, simply because this is bigger. Since this is non-positive, this is smaller than 1, so this inequality is trivial. And now we use the lemma, the lemma, Uchiyama's lemma. Then we use here Uchiyama's lemma, and we obtain this inequality. And then coming from here to here is just to write things properly. So we get the lemma. This is what we call the basic lemma. So let's see. The basic lemma. Something happened here. This is a stop. Let me see. This happened also yesterday. Let me see if I can get this again. Okay. So this is the lemma that we prove. The basic result, the integral of mod f prime squared times h, the absolute value times this log, is bounded by the h1 naught of f times the BMO naught of big F. This is the basic. And then let's see how do we obtain the duality. Well, the first thing we use the Littlewood-Paley identities, which this can be obtained either using Green's theorem or just using Parseval identities. If we have two functions, f and h in H2, and then, well, I have subtracted here f of 0, but maybe later on I forget about f of 0, and I think that f of 0 equals 0. But anyway, this is simply the Parseval identities, or if you prefer the by Green's theorem, we get this Littlewood-Paley inequalities. Then using this, what I call the basic result for duality and the Cauchy-Schwarz inequality, what we get is this. If we start with a function f, this function f, the big F is in BMO, H is in H1. Then we use this. Let's forget about the f of 0 and g of 0. So then we use this. From this, we obtain this, and then we just put absolute value inside. And from here to here, we simply use the Cauchy-Schwarz inequality. Cauchy-Schwarz inequality, writing this as h prime to the 1/2 times h prime to the 1/2. The 1/2 to a square comes here, and the other one comes here. Okay. So then what we get is, but the test that we have here is by the Hardy-Stein inequality that I stated in the beginning, is majorized by the H1 naught of H. So what we get this result. We put this and this together, and this gives the BMO naught of F times the H1 naught of H, which is what we wanted to do. So we have proved the base, what I call the basic result of the basic result that we have here about duality, which is this. Okay, but then using the Parseval identity, then what we get is. But now that once that we have obtained this for a function f in BMO and a function g in H2, then this is easy, because what we do, if we take a function f instead of being in H1, we take it instead of being in H2, we take sorry, this here is a misprint. What I mean is that the function f is in BMO, and the function g, we take the function g in H1. Then if we take the function g in H1, we approximate it by the function g sub r of z, which is g of r z. We apply the previous lemma, and then we get this approximation, and then in this way we get the result that we wanted, that the limit before exists. So using this, we get this. Let's some remarks. The limit that we assert that it exists in the theorem can be written, of course, in terms of the Taylor coefficient. If the function f is the sum of a n c n and g is the sum of b n c n, then this limit is simply the limit of a n bar bn times r. This is the first remark that I want to say, because and the second remark is that the duality theorem says that this limit exists, but if f is in BMO and g is in H1, I should remark that one could think that this integral actually converges, or if you prefer, that this sum a n bar times b bn this series converges, but this is not true. This integral may not be converged for if f is in BMO and g is in H1. Okay, so actually, you remember that when we were speaking on Hardy spaces, the dual of HP was HQ, and the duality pairing was the integral of f times g. But actually, the integral of f times g I theta, when r equal 1, if we put r equal 1 here, this integral may not converge. Okay, this can be proved using, I don't know, or closed graph theorem or something, but actually, it's possible to give an explicit example. Let's see, an explicit example could be if we take. Let's say the simple BMO function, if we take this This is in BMO. Maybe we can take as G. Let's see. If I take 1 minus Z, and then I put here log of say 2 over 1 minus Z squared, this function G is in H1. Yeah, in H1, sorry. And for this function, one can more or less, I think it's not difficult to prove that if we take this integral, f I theta times g I theta, this integral does not converge. Okay, so actually the theorem says is precise, and we cannot substitute this limit as r tends to 1 by the integral over the boundary. Okay, let's see, let's come back here. Okay, let's go back to what I called the basic result for duality. The basic result for duality, that what I call basic result for duality was this: that if we have a function f in BMO and a function h in H1, then we have that this integral is bounded by the product of the H1 node of H and the BMO node of H. But now let us look at to this inequality in this way. Consider the measure d mu of Z equal log of 1 over absolute value of Z times f prime of Z squared dAZ. So this thing here, the f prime squared, and then this measure. So if we take a look at this, and then this inequality here can be seen in the following way: that if we take any function h in H1, if we integrate h against this measure, then we get something which is finite. So this means that H1 is contained in L1 of D with this measure. And if then we use Carleson's theorem, we know that this inclusion holds if and only if the measure is a Carleson measure. Well, I guess I haven't defined what Carleson measure is, but you all know what the Carleson measure is. Okay, if we have a disk, I think that Nicolas Salmokis spoke yesterday about it. You have a disk, you have any interval I, and then you take the Carleson box. The Carleson box, I mean that this length is comparable to the length of I. A positive measure in the disk is a Carleson measure. We call this the Carleson box. Let's say call it this is SI. Mu is a Carleson measure means that mu of SI is smaller than the measure of I for an absolute constant for any I in that. So and then what we have, if we use Carleson's theorem, Carleson invariant theorem, since we have that if f is in BMO, we have this inclusion, then this means that this measure is a Carleson measure. But now recall that log of 1 over absolute value of Z is comparable with 1 minus mod C squared as mod Z tends to 1. So using this, what we get is that if f is in BMO, then this measure, we can substitute this logarithmic term by 1 minus mod C squared is a Carleson measure. So we get this. If we use the duality theorem, we get the converse. So actually what we have is that the function f is in BMO A if and only the measure 1 minus mod C squared times absolute value of f prime of Z squared dAZ is a Carleson. There is I was very fast in the let's say in what I call the easy part of the duality theory, but I said that in the proof what we did is actually we proved that the function f was in BMO could be written in this part. So actually, if one uses the duality theorem and look at the proof of the first part, then actually we obtain also that the function a function which is analytic in the list is in BMO if and only it can be written as f1 plus if2 with f1 and f2 with positive with bounded real part. So more or less, this is an idea of the proof of the Pfefferman's duality theorem. Well, I'm going to speak very quickly about VMO and VMOA. I guess that Nicolas here, Charmokis spoke a little bit about them yesterday. I'm just going to define them, and I'm not going to say much. VMO and VMOA are the little O version of VMO and VMOA. So a function f which is in VMO is in VMO. V comes from vanishing mean oscillation. If VMO was that the supremum overall or interval of these oscillations was bounded. So VMO, vanishing mean oscillation, means that if we take the limit as the length of I tends to 0, this oscillation, that limit is 0. And in a similar way, when we go to the analytic VMO space, recall that one of the characterization of VMO was that the family of the composition of F with all the conformal mappings of the disk into itself, and we subtract the value of F at A, that this was a bounded subset of in HP. Well, if we substitute this being bounded by the limit as absolute value of A tends to 1, this is 0, then we get what we call VMO, vanishing, analytic vanishing mean oscillation. VMO is a closed subspace of VMO, and actually it is the closure of the polynomials in VMO. Nicolas Charmokis told us that VMO was, Sarason proved that function f in VMO is in VMO if and only if when we compose f inside with rotation, then we let that rotation tends to either the identity that composition tends to F, and this was solved by Sarason also. And in many ways, VMOA plays the role with respect to VMO as the little block space play the role with respect to V. The little block space is the function is the little block space is the limit as mod z tends to 1 of 1 minus mod c squared times the absolute value of f prime of z tends to 0. In the same way, the little block space is the closure of the polynomials in the block node. And actually, we had that this algebra is contained in VMOA and contained in the little block space. I should say that the Pfefferman's duality theorem that I stated, that the dual of H1 is VMO, can be complemented saying that the dual of VMOA is central. But I'm not going to get into details. Let's see. And then now that we have more or less studied a little bit the spaces VMOA, and we have proved the two basic results that I said that are the connection of VMO with analytic functions, so that the substitute on the enriched conjugation theorem for P equal infinity and this Pfefferman's duality theorem, then what we try to do is to study a little bit the structure of the space. Well, whenever we have a space of analytic functions, one of the things that we try to do is to know a little bit, to know what are the zeros of function in this space, what are some operators on this space, and so on. If you remember, when we in one of the in some of the courses that were given in this program, there was a course in Berman spaces, and there was a course in Dirichlet spaces. And in those courses, you remember that one of the sections was studying the zeros of function in those spaces. In both cases, the set of zeros were not the Blaschke sequence, were different from the Blaschke sequence. However, if we can here with BMO, what do we have here? BMO, we know that contains H infinity and is contained in all Hardy spaces HP with P equal infinity. Since the zero set of H infinity are the Blasquez sequence, are the zero set of any Hardy space P, when P is equal to infinity, is smaller than infinity, sorry, then what we have is that the zero sets of BMO are the Blasquez sequence. So in this case, there is no difference with the zero set of Hardy space. If we have, and of course, any Blasquez product is a member of BMO. It's a bounded analytic function, so any Blasquez product is in B. Actually, one can prove that the BMO node, if we take the conformally invariant node of any Blasquez product, then one can compute it. And actually, it's always, if we forget f of 0, all the Blasquez products have BMO node equal to 1 plus B of 0, but this works when P is smaller than 2. When P is, actually, we have written here this for Blasquez product. Actually, this can be extended, and this is true for any inner function. And if we have an inner function, we call that this H infinity norm, whose boundary values have absolute value equal to 1 almost everywhere. For any inner function, we can prove that the BMO node of that inner function is exactly this. But this works only for P smaller than or equal to 2. I think that in June, I don't know, in June, July, Stamatis Pouliasis gave a talk, I think, and he made a conjecture, and that conjecture, or some result, he proved some result, and he was able to prove with the BMO AP node for P smaller than 2, and the question for P bigger than 2 was open. He conjectured a bit, but it's open. And then, I don't know, we spoke a little bit, and I told him there are a lot of questions in BMO where the things changes when we consider this nodes for P smaller than 2 and for P bigger than 2. Actually, this is one of those. This is all that I write here is for P smaller than 2, but if we go for P bigger than 2, the result is not true, because actually what we can is true, and it is not difficult to prove, is that we take large values of P, then this BMO node, the conformal invariant P node of I is equal to this plus 2 for when P is in the limit, when P goes to infinity, this is 2. So this is one of those examples of questions we have to do with BMO where the things are different if we consider the conformally invariant node corresponding to P smaller than 2 or to P bigger than 2. We will find some other examples of this situation later. So the question about the zeros of function in BMO is completely solved. Are simply Blasquez sequence. Of course, all the Blasquez products are in BMO. However, if we consider VMO, the VMO vanishing mean oscillation, what happens is that only the final Blasquez product lie in VMO. Of course, any final Blasquez product belongs to VMO because a final Blasquez product is in the disk algebra. It's continuous in the closed unit disk, but they are the only one in VMO. Actually, it's true because if we have an infinite Blasquez product, and these are the zeros of the Blasquez product, then if we take B and we compose with CAN and we subtract, this is 0. So this is simply this. But if we compose a Blasquez product with this is again an inner function, and so the HP node of this is 1, and then this is 1. So actually, so this does not tend to 0. But if this does not tend to 0, so we have that the product is not in VMO. So the finite Blasquez product are the only one in VMO. Actually, this can be extended and saying that final Blasker products are the only inner function in VMO. What we need to use here is that if we have a non-constant inner function, then it takes values arbitrarily small. And so then using this an argument more or less like this, then we can extend this result, considering not Blasker product, but inner function. The final Blasker product are the only inner function which lies in there. Anyway, there is some difference. I said that VMO and the little block space play a role similar. The relation between block and the little block space and VMO and VMOA are very closely related, but I should remark that this result for the little block space is not true. Actually, it's a famous result of Saracen, that there are infinite Blasker products in the little block space. So here we have a difference in the little, while in VMOA we don't have any infinite Blasker products. Saracen proved that this is not true for the little block space. There are infinite Blasker products in the little block space. Okay, so let's see. Well, let's speak a little bit about multipliers. I have said that any Blasker product is in VMO because VMO H infinity is contained in VMO. But what happens if we let's start with this question. What happens if we have a function in VMO and we multiply it by a Blasker product? Can we say something? Well, we can speak a little bit more general and speaking about multipliers. This definition, you all know the definition. If you have a Banach space of analytic function, that I'm not going to say, but whenever I say that X is a Banach space of analytic function, I'm going to assume that is continuously embedded in the space of holomorphic function. I mean that convergence in node implies uniform convergence encompass a set, and I will also assume that X contains all the polynomials, so that we don't get a trivial thing. So if we have a Banach space of analytic function, a function F analytic in the disk is going to set to be a multiplier. I would say pointwise multiplier, because as you know, we can speak also of Hardeman multipliers. So let's say pointwise multipliers if whenever we have a function g in X, the product of F times E is in X. And the space of all multipliers is usually denoted by X. It's something quite standard that the space of multipliers of a Banach space that is fine those conditions that I have said, that contains all the polynomials and is continually embedded in the space of holomorphic function in the disk. But for any space, we have that the multiplier, the space of multipliers is contained in H. And I think that in the courses given previously regarding Hardy spaces and Berman space, this question was considered, and over there it was said that the multipliers of any Hardy space and also any of the Berman spaces, AP alpha is exactly H infinity. And then we can think about VMO, which is what I said in the beginning. More than considering the general question, let's start with Blasker product. We know that all Blasker products lie in VMO. But if we multiply a function in VMO by a Blasker product, can we say something? Well, the thing is that we cannot say it. Let's work with the typical example of a VMO function, the function log of 1 over 1 minus x. And let's take a quite simple Blasker product, the Blasker product which has zeros at 1 minus 2 to the minus n. So this is an exponential sequence. So the Blasker product whose zeros is this, which is an exponential sequence. And then we consider the product of b times the log of c. So this function is with VMO. This is a Blasker product. However, the product is not in VMO. Actually, it's not a block function. Why is this? This is easy because since this is exponential sequence, it is uniformly separated. I'm not going to explain it, but uniformly separated means that this there exists a positive delta such that 1 minus mod an squared b prime of an is bigger than delta for all. And then it's just a computation. If we take here, we take the derivative of this times this is b prime times log, b prime times log, but the other term that we get when we apply the rule for the product is b in an times the derivative of it, but since b of an is 0, then that term disappears. So what we have is this. But since we have that this is bigger than delta, the product of this times this is bigger than delta, so this tends to infinity. So in this way, we get that this is not a block function. Actually, this idea, I guess, goes back to Lapan in the 1960s. The idea here can be generalized, and actually one can prove easily the following: that if we have a function, any function f, analytic in the disk, and which is not bounded, then we can find an interpolating Blasquez-Prada. Interpolating Blasquez-Prada means, and I'm not going to get into details, this has to do with the problem of Carleson interpolation, but let's say in interpolating Blasquez-Prada, this one will satisfy it. Maybe we can. Okay, there exists an interpolating Blasquez-Prada such that the product of b times f is not a block function. So, and actually, with this kind of ideas, one can prove that this. Okay, for sometimes, well, I guess that the explicit examples of function in BMO, so that multiplying by a certain function is not in BMO, I guess the more simple example that I knew were of this kind, a Blasquez-Prada, and actually an interpolating Blasquez-Prada times a function in BMO. Actually, I guess a couple of years ago or so, I think it was Joe Zimmer sent me a message asking if we can do something similar. He was interested in something, and he needed to estimate the product of a certain BMO function with the singular inner function, the 1 point mass in singular function. And he asked me if I knew what can be done. Then I was thinking a little bit, and then I was able to prove that if we have the singular inner function with point mass here, so the S of C equals the exponential of -1 plus Z over 1 minus Z, and we take any function f, we satisfy this. And this is a, let's say that the function log of 1 over 1 minus Z satisfy, of course, these two conditions. So if we take the product of this function log of 1 over 1 minus it times this singular inner function, then we get also that this function is not a block function. So we have two kind of examples. We have, in the first example, is a interpolating Blasquez-Prada times a BMO function, which is not a BMO function. And in this case, what we have is this singular inner function times a BMO function, which is not a BMO. Maybe this is a result that I proved in collaboration with two colleagues from Málaga, José Ángel Peláez and Cristóbal González. Maybe this is a little bit more surprising, because here is a construction of the same kind, that we have a Blasquez-Prada, but here we don't ask the Blasquez-Prada to be interpolated. The only thing that we ask is that the zeros is contained in the radio. We take a function g, so that g of z tends to infinity as z tends to 1. For instance, g can be, again, the function log of 1 over 1 minus z. Then in this situation, the product of b times g is not in BMO. Actually, one can prove that it's not a block function. Well, I should say a little bit. The example, the preceding example, this one and the one involving the interpolating Blasquez-Prada, we can prove something stronger than this. We can prove that this function big F is not a normal function, but I prefer not to introduce it and just say here. However, here in this theorem, we are not able to prove that this product is not a normal function. We simply prove in this case that we will have a Blaschke product with zeros in radius, and an analytic function like this, which tends to infinity as we go to 1, this product is not enough. So let's see. Anyway, we have obtained a number of examples of functions which are Blaschke product or this singular inner function, so that they are not multipliers of Bn. But all these examples are, as I have said, either Blaschke product or either this singular inner function. They are, let's say, bad behaved in the boundary. Okay, so this example that I have given so far are somewhat bad behaved on the boundary. They have some singularity. Either there is some sequence of zeros, which of course tends to the boundary, or this singular inner, the Pointwise inner function also has some singularity in the boundary. What happens if we consider regular H-infinity functions? Let's say we consider an analytic function which is in this algebra. Can we say something? Well, in the positive sense, we can say something. If we have, for instance, some function which is in the class lambda alpha, let's say lambda alpha means that if it's analytic in the disk and say continuous in the closed unit disk, and so that the boundaries values satisfy a Lipschitz condition of order alpha. Or you prefer if it is in the mean Lipschitz space lambda p alpha, this means that F is in HP and the modulus of continuity of order P satisfies the certain growth. Yeah? So if we have this, maybe forget about this. If we have some function in this lambda alpha, if one uses the characterization of VMO in terms of Carlson measure that I gave a few minutes ago, then it is easy to prove that actually this function in this space are multipliers of VMO. But let's see, then once that we notice this, then we try to think if we have some not so much regularities, something a little bit less regularity. Then I thought, what can we say if we consider lambda 1, 1? Lambda 1, 1 is the space of analytic function, so that F prime is in H1, or even some space which is even smaller than this, the minimal space V1. This is the space of function analytic in the disk, so that the second derivative is in the Berman space S1, so that the integral over the disk of the absolute value of the second derivative of F is finite. This is a very small space. This is the minimal space. It is called minimal because it is the minimal conformally invariant space. Among all the spaces of analytic function in the disk which are conformally invariant, this is, well, let's say natural, which has some natural. This is the smallest one. The block function is the biggest one, and this is the smallest one. So this is a very small space. So then we were thinking, and then the question which came to my mind is, can we say if we have a function here, or maybe even here, can we say that it is a multiplier of the space, just as what happens with this function in this Lipschitz space? So actually, the answer was negative. Actually, I guess 1 year ago or so, I was able to prove that if we have a function which is a block function, a non-bounded block function, then we can take a function which is in this minimal space, such that the product F times D is not a block function. So in particular, this smaller minimal spaces contains a function which are not, but these are, let's say, constructive examples. Anyway, what I should say is that a characterization of the multipliers of VMO is known, and I guess it was first obtained by Ortega and Fábrega. And this is characterization. The thing is that the function G analytic in the disk is a multiplier if and only if G is in H infinity. We know that the multipliers of VMO has to be in H infinity. In general, for any space X the multipliers of x are contained in H infinity, but it has to satisfy also this extra condition. See, so this is the characteristic. I'm not going to get into the proof, but the thing is that anyway, this condition is not so completely easy to check on concrete examples. So, so over the years we have been working on seeing special classes of functions so that we can say, and we have obtained a number of results like this in more or less in the negative way, and someone is the positive one also. Okay, let's see. Well, let's see. I have said that Blaschke product or inner function are not, in general, are not multipliers. There are Blaschke products. Say there are Blaschke products which are not multipliers. So BMO does not behave well when we multiply by a Blaschke product. However, we can think not about multiplying a function by a Blaschke product, but dividing. And the thing is that Blaschke products are good divisors of BMO functions. Let me explain a little bit and introduce a little bit the terminology. In general, if we have a space X of H1, as a space X of H1, the terminology is the following. It's said to have the property of division by inner function. It's called also the F property. If whenever we have a function, whenever we have a function f in X and I inner function, so that when we divide f by I, we are in H1, then actually we lie in X. So when this happens, we say, and when this happens always for any inner function with this property, we say that f has the property of division by inner function. So let's say that if a function can be divided by inner function within H1, then it can be divided by that inner function within X. And well, the spaces, the Hardy H1 or the Hardy spaces HP, of course, have this property. And there are a lot of spaces which have this property. And in fact, it is possible to prove that BMO and VMO have the F property. And even a stronger one that I'm not going to speak about, one which is called the K property, but I'm not going. And this can be proved in several ways. It can be proved using duality, using the NOR, the conformal invariant NOR, and so on. This is not difficult to prove, but I should mention that BMO and VMO. However, since I said that there is a close relation between BMO and the block space and VMO and the little block space, I should emphasize that what happens with the block space. Well, I said before that Saracen proved that there are infinite Blaschke products in B naught. Then using that, it's relatively easy to prove that if we consider B naught, well, B naught is VMO, and VMO, of course, are subspaces of H1. The little block space is not. So if we want to speak about this property of division by inner function, we have to consider the intersection with something. So let's take the intersection of B naught with H infinity. So the intersection of B naught with H infinity does not have the F property. Let's say this is easy, as I said, this is an easy consequence of this result by Sarah. So we have a Blaschke, an infinite Blaschke product in B naught. Then take AN as subsequence of the sequence of zeros, or the sequence of zeros of B, and so that AN is interpolated. Say, for instance, exponential. And then let's take B1 is going to be the set of zeros, the Blaschke product whose zeros is this sequence, B. And B2, the complement, the B2, the Blaschke product with the other zero. then of course B is B1 times B2. But if we take B over B2, this is B1. And this is an interpolating Blaschke product, so this B1 is not infinite. Also, so this is easy, it's quite easy to prove that, as I said, that the space, let's see, the space B0 intersection H infinity does not have the property. This was first proved by Milne Anderson. And a few years ago, we were thinking, what happens if we don't consider here B0, but we consider the Bloch space? And actually, in a working collaboration with whom? Cristóbal González and José Ángel Peláez, two colleagues from the University of Málaga, actually we were able to prove that B, if we take B intersection any of the Hardy spaces with P less than infinity, this also fails to have the property, does not have the property of division by inference. Okay. So I guess, yeah, I guess I should, is 1652. So I guess I should quit here. So let's, okay.
Thank you, Daniel.
Mm-hmm.
Let's take this week. Any question or comment for Daniel?
I have one. Bill Roth, you talked about the multipliers of BMOA. Are there any known results about the multipliers of BMO without the A?
Yes, there are the things that I hear. I'm always thinking on analytic spaces, but there are the results. Actually, the result that I have written, Ortega Fabregas result that I have written about BMO, this can be rewritten for multipliers of BMO.
So there's a non-analytic.
Yeah.
Oh, okay. What about VMO?
About VMO?
Yeah.
Well, the result that I'm not sure. I guess that they are also known. There is a characterization. I guess that there is a characterization, but right now I cannot.
Okay.
But I guess that there is a characterization.
All right. Thanks.
Okay.
But then explore a bit the question of Bill. They are not of the geometric characterization in the sense of Carlson or Estaganga that.
Yeah.
Do we have any characterization of
no,
this?
Some characterization of that kind is what I mean. Okay. But not, this is what I said. The characterization that one knows is a very nice characterization, but at the end it's difficult to check whether a function is a multiplier or not. Then when we take this result that I have mentioned on Blaschke product and so on, some of them would be difficult to check whether they satisfy this condition. So that, okay, but this happens many times with this kind of characterization, which are good characterization, but at the end it's difficult to try to check whether a concrete function satisfies that condition or not. Okay.
Thank you. Any further comment or question for Daniel?
Hi. Sorry, I had a question about your proof for the duality. It was very nice that you said it's due to Knesset.
Yes.
So this is not what you sent in the notes, right? This is a different proof.
No. In the notes, I have sent two files. One is a file of something that I wrote 20 years ago, but then I sent also the transparency that I'm using, and then in this transparency you can find that.
Oh, okay. How do we get the transparency?
It's in the chat. I uploaded them in the chat. But anyway, I can send you again if you.
Okay, I don't get any.
I didn't get it either.
You don't get, so maybe I uploaded them in the beginning. So maybe Anyway, I will try to upload them again because I
Yes.
guess that 1 month ago it happens that if somebody enters into the reunion after I send, maybe they cannot.
Yes.
So I will upload them now. Okay. Okay.
Okay, thanks. Yeah, I thought it was very interesting because it's basically in the real Hardy BMO cases what's done in Pfeffer and Stein when they go into the upper half space and do the.
Sure. Yeah. This can be done in the half plane also. This is more or less the same. Okay.
Thank you.
So I will try to upload this again now. Okay. Now let's see if I can do it because I was able once. I will try it. Okay.
Thank you, Daniel. So let's thank the speaker again. And we appreciate if you